Something strange is happening in the soil at the Hoh River Valley in Washington state. Not salt spray, not tidal flooding, something that smells distinctly of the ocean, carried here by an animal that swims 1,000 miles to die at the roots of these trees. Fish bones in the undergrowth, claw marks on fallen logs, the forest floor scattered with the remains of Pacific salmon miles from the nearest coast. What looks like death, thousands of rotting fish carcasses in shallow streams, is actually the most important nutrient delivery system these forests have ever known. This is not decomposition. It is nutrient engineering across ecosystem boundaries. The old-growth forests of the Pacific Northwest are among the most productive on Earth. Sitka spruce and western red cedar tower over 60 meters. The structural complexity of these forests is unmatched anywhere in the temperate world. But the soil alone cannot explain their growth. Nitrogen levels in Pacific Northwest soils are consistently lower than what these growth rates demand. The missing piece is not geological, it is biological, and it swims upstream every autumn. For thousands of years, Pacific salmon runs numbered in the hundreds of millions. Every autumn, rivers turned silver with returning fish. Each salmon carried kilograms of ocean-derived nitrogen and phosphorus in its tissues, accumulated over years of feeding in the North Pacific. Then the runs collapsed. Commercial fishing, hydroelectric dams, and logging stripped spawning habitat across the region. Salmon populations declined by more than 90% in many watersheds. Some runs disappeared entirely. The rivers fell quiet, and the forests on their banks began measurably to change. In the early 1990s, researchers at the University of Washington began a 20-year study tracking marine-derived nitrogen in these forests. The tool was straightforward. Ocean nitrogen carries a distinct isotopic signature that differs measurably from terrestrial nitrogen. By sampling tree rings, soil cores, and insects, researchers could trace exactly where the nitrogen originated. The salmon are doing soil fertilization that nobody asked them to do. Here is the mechanism. Pacific salmon spawn once and die. A single Chinook carries roughly 130 grams of nitrogen in its body. When it dies in a shallow gravel bed, those nutrients enter the stream directly. Bacteria colonize the carcass within hours. Dissolved nitrogen seeps into the surrounding soil. Bears amplify this process deliberately. Grizzlies and black bears catch salmon, eat the brain and roe, then drag the carcasses up to 500 meters from the water into the forest. A single bear transports dozens of carcasses per day during peak spawning. Blowflies and beetles then break down the remains, excreting nitrogen in forms directly available to tree roots. Mycorrhizal fungi carry these nutrients to surrounding root systems. The result is measurable. Trees within 50 meters of salmon streams show up to 80% marine-derived nitrogen in their tissues. Trees in salmon zones grow up to 3 times faster than comparable trees without salmon. 137 species depend on this nutrient cycle. Before we get into what the long-term data showed, if you are enjoying this so far, please consider liking and subscribing. It genuinely helps us make more videos like this one, and it only takes a second. Now, back to the story. The 20-year dataset confirmed it. Tree ring analysis revealed that marine nitrogen signatures correspond directly to historical salmon abundance. In years when runs were large, nitrogen-15 isotope ratios spiked. When runs declined, the signature dropped. The trees were recording salmon runs in their growth rings, a chemical archive spanning centuries. Salmon once delivered approximately 130 million kilograms of nitrogen and phosphorus to these forests annually. With populations at a fraction of historic levels, forests downstream of major dams show measurably lower marine nitrogen than forests along free-flowing rivers. The ecological cascade is running in reverse. Could restoring salmon runs disrupt ecosystems that adapted to their absence? Neither side of this argument wins cleanly. On the ELWHA River, 2 dams were removed between 2011 and 2014. within 5 years, salmon returned to reaches blocked for over a century. Vegetation recovered, insect diversity increased, and the cascade was restarting. However, the Elwha removal cost over $325 million. Dams on the Snake River power hundreds of thousands of homes. Fishing communities worry wild restoration could undermine managed fisheries. Tribal nations consistently advocate for dam removal, but political resistance remains substantial. These are disturbance engineers whose absence compounds over decades. The restoration effort continues. The debate continues around it. Salmon are not just fish. They are the mechanism by which the ocean feeds the forest. Their decline has been measurable in tree rings, in soil chemistry, and in the thinning canopies above rivers that once ran silver every autumn. What do you think? Should we tear down dams to restore salmon runs, or is the energy cost too high? Leave your answer in the comments. Subscribe so you do not miss the next one.